This session is about cylinders. Now that we have discussed about surface areas and volumes, let's now enter into understanding what is a cylinder. As we have seen this real life model, I see that this CD stand clearly has various different CDs lined out on the rod. Now if I take one CD out from this, it looks like a circle. So I see this CD stand to be a set of all circles built up so that it forms a three-dimensional shape. So let's understand a cylinder through the concept of the CDs. So a circle, as in this model, when I take and I put another circle or a 1 rupee coin or a CD, as we have seen in this model, one over the other, we see that the different types of CDs as built forms a sort of a shape which looks like this. And this kind of a shape as formed by these CDs is nothing but a cylinder. So in mathematics, the set of infinite circles built on each other to form a cylinder is how we understand through the mathematical means. Now let's try to make it more brief about a cylinder. As we have seen, the different sets of circles but provided if I take two different CDs, I see that the two CDs are equal in size. The two CDs do not have different sizes, but the two circles are assumed to be of the same size. The rule for constructing a perfect cylinder is that all the set of infinite circles must have same size. This is how we understand the important means of constructing a cylinder. So as we come through the model, I see that all the cylinders, all the circles which form the cylinder have the same size, and therefore it constructs a straight figure which is called a cylinder. Different set of circles of same size to be noted down form something like a three-dimensional object which is called a cylinder. So cylinder built from different set of circles constructed on each other, of course of the same size. This session is about understanding what a right circular cylinder is. Now that we have understood the cylinder to be constructed from set of circles, let's now try to understand the most important part of cylinder, which is called right circular cylinder in mathematics. This session is about right circular cylinder. What is a right circular cylinder? What is the difference between a cylinder and the specific cylinder given by the name right circular cylinder? So let's see this in brief. So as I see right circular cylinder, I have three different things which I understand: the one which is right, the one which is circular, and the one which is, of course, a cylinder. Circular and cylinder. So we differentiate a right circular cylinder into three classifications. One is this, this, and this. Let's understand each of this to understand the whole concept of right circular cylinder. As we see, right in mathematics means the one which is at right angle or 90 degrees is how we understand a cylinder. A cylinder which is exactly straight as 90 degrees is called a right circular cylinder. And of course, the cylinder must be circular. It cannot have a different shape other than each of the circles being constructed to form a cylinder. And circular at every stage. Every stage and equal in size is how we understand circular. And of course, it must be the shape of a cylinder, as we have seen in the previous model of the shape of a cylinder. So this is how it looks. It must be cylindrical in shape, as this we see as a cylindrical shape. Therefore, a right circular cylinder is a three-dimensional solid which is in the cylindrical shape and which has circles which are equal in size at every stage. I take a CD here or any stage of, they are equal in size. So circular at every stage and equal in size. Right, that is, it must be exactly 90 degrees to the ground. If the cylinder is cross, then we say it is not a right circular cylinder. The angle between the ground and the height at which the CDs rise must be 90 degrees. Right angle or 90 degrees is how we see a perfect cylinder. That's how I have the base, which must be exactly from the ground at 90 degrees. Cylinder, which is right circular, has three important classifications. Right circular cylinder. Now that we have identified the definition of a right circular cylinder, let's see some of the objects which are right circular and which are not right circular. For example, I take a cylinder which is crossed. It is crossed out here, and then this kind of a cylinder cannot be right circular because the angle between the ground and the height at which the cylinder rises is not 90 degrees. That is, if I take this to be a ground, then this angle is theta, and here this angle is not equal to 90 degrees. Is how mathematically we identify a right circular cylinder. The angle between the ground and the height at which the cylinder rises must be 90 for the cylinder to be right circular cylinder. Theta is not 90 degrees. Therefore, the given cylinder is not a right circular cylinder. Since theta is not 90 degrees, therefore the given cylinder is not a right circular cylinder. Is how we understand. Let's take one more example to understand the classification between right circular and a non-right circular cylinder. For example, I take a shape which looks like a cylinder, but actually this solid is formed by constructing a different object which is in the shape of this. So each of a shape which is not a circle is constructed. If the shape, something which is like this, is used to construct, just like an egg shape, so this is an egg shape which is constructed, then this cannot be a cylinder, right circular cylinder, because we demand for circular concept in right circular cylinder. So if this is egg shape, then this is not a right circular cylinder. Though it is 90 degrees from the ground, it cannot be right circular cylinder because it has to be a circles which are constructed to form a cylinder. The reason being, each of the constructed objects are egg-shaped, is how we understand the right circular cylinder demanding for three different rules: this, this, and this. Now let's see one more solid object to understand right circular cylinder concept more stronger. Suppose I have a circular cylinder which bulges out here like this. This seems to look like a cylinder, but this is not right circular, though it is 90 degrees from the ground. And though I see this 90 degrees from the ground and I see this being a circle, still I say this is not right circular cylinder, because each of the circles as constructed in the cylinder are not of same size. So here it is very important to note that this kind of a cylinder cannot be right circular cylinder. This is not a right circular cylinder, as each of the circles as constructed to form a cylinder are not of same size. This is the main reason why this cylinder does not become a right circular cylinder. This is not a right circular cylinder, as each of the circles as constructed to form a cylinder are not of same size. They must be of same size. This is a perfect right circular cylinder because each of the CD of the same size is constructed to form a cylinder. Circle of same size makes a solid right circular cylinder. So now that we have discussed about a cylinder and a special case of a right circular cylinder, it is very important to note that unless otherwise stated, a cylinder is assumed to be a right circular cylinder. So in the syllabus, when we refer to the notation and terminology of understanding the cylinder, we understand that unless otherwise stated, a cylinder as mentioned in the topic refers to. So we indirectly refer to any problem related to the word cylinder is assumed to be right circular cylinder unless otherwise stated with something else. Refers to right circular cylinder is how we understand the notation and terminology in cylinder concept. Cylinder assumed to be right circular cylinder unless otherwise stated. Now that we have discussed about cylinder and its special case as a right circular cylinder, now let's see how a cylinder is constructed from a rectangle. This is quite interesting because if I have this rectangle out here on the plain whiteboard, how do I construct a cylinder from this rectangle as taken? So imagine this sheet of paper which is rectangular length and width of certain dimensions. If I roll this exactly, if I just roll out here, it forms a cylinder. We assume that this paper which is rolled forms a cylinder. Out here and down out here, it's open. So a cylinder formed through a rectangular sheet of paper is how we're going to understand. So this session is about understanding the construction of a cylinder from a rectangular sheet of paper. cylinder from a rectangular sheet. As we have seen, a rectangular sheet of paper, when rolled, forms a cylinder. It is very important to note that a cylinder which is formed from a rectangular sheet of paper is understood to be with what could be the length of the cylinder when compared to the rectangle. If the rectangle has the dimensions length and breadth, what could be the length of the cylinder is the biggest question. So here, when I take the sheet of paper like this, I have my height, which is nothing but the breadth. The breadth of the rectangle will be the height of the cylinder, because as clearly seen, we have this is length and this is breadth. So when I roll this cylinder, it is nothing but the height remains constant, doesn't change. That is, the breadth of the rectangle when rolled forms a cylinder of height with the same dimension as B. So the breadth of the rectangle will be the breadth or the height of the cylinder. So first thing we note is the breadth of the rectangular sheet is the height of the cylinder formed. As can be clearly seen here, the breadth of the rectangle is the height of the cylinder as formed. And the length of the rectangle, let's see what happens to the length of the rectangle. As we just take this and roll, this length of the rectangle forms to become the circumference of the circle. So here, the second point which I identify is that the length of the rectangular sheet, the length of the rectangular sheet is the circumference of the cylinder, that is the circular region formed. So the length of the rectangular sheet is the circumference, as can be seen here. This is the circumference forms with the length of the rectangle. So breadth becomes the height of the cylinder and the length becomes the circumference of the cylinder. So let's see how they are related. But the same sheet of paper, which is a rectangle, now becomes a cylinder. The same rectangular sheet now becomes a cylinder, is the cylinder, curved and with a circle. Now that we have discussed about a cylinder which is derived from a rectangular sheet of paper, now let's see what could be the surface area of a cylinder. The topic says surface areas and volumes, and hence, now that we have discussed about cylinder, let's see what is the surface area of a cylinder. So in this case, I see that a rectangular sheet with, let's see, the curved surface area of a cylinder. Let's come back to the rectangular sheet of paper when rolled forms a cylinder. Therefore, the same area as occupied by the sheet of paper will be the same area as occupied by the curved region of the cylinder. Is how we understand the same sheet of paper occupying the same surface area when it forms a cylinder. So therefore, here we identify that surface area of a rectangle, of a rectangular sheet of paper is equal to the same curved surface area of a cylinder. Curved surface area of a cylinder formed from it. So this cylinder is formed from it. So surface area of a rectangular sheet of paper is nothing but curved surface area of a cylinder. So when we want to find curved surface area of a cylinder, we connect that with area of rectangle. So here, curved surface area, which I denote by CSA, of a cylinder is nothing but area of rectangle, that is length into breadth. But my length, which forms the circumference, as seen in the previous case, this gives me the circumference 2 pi r and this gives me the height h. So length becomes 2 pi r and the breadth becomes height. Therefore, CSA of a cylinder is 2 pi r h unit square. Is how we understand the curved surface area of a cylinder. If this is a cylinder, the curved surface area is only the curved part but not including the top and bottom. So curved surface area of a cylinder is 2 pi r h unit square. Pi is 3.14, r is the radius and h is the height. So r is the radius of the circle and h is the height of the cylinder. Is how we understand curved surface area of a cylinder, 2 pi r h. Now that we have discussed about curved surface area, there are other possibilities. What if I take a cylinder which is closed both on the top and the bottom lid? What if I have a cylinder which has a lid which is closed? So let's take the different cases of a closed cylinder. So this session is about finding the total surface area of a closed cylinder. So imagine I take a cylinder not here, and the radius of the cylinder say is r and the height is h. Now here the difference is that this cylinder is closed both at the top and bottom. So this is a closed cylinder. This is a cylinder which is closed both at the top and bottom. So here it is closed and even down the cylinder is closed. So a cylinder which is closed on the top and bottom. Let's see what could be the surface area of this kind of a cylinder. So here we have total surface area of the cylinder is 2 pi r h, because it is nothing but the curved surface area, which is the curved part, plus the top and the bottom. Like for example, I take this, the total surface area is the curved surface area plus the top surface and the bottom surface. So we take into inclusion all the three regions, the curved part plus area of circle or top circle and area of bottom circle. So curved surface, area of top circle and area of bottom circle. So I get this to be 2 pi r h plus pi r square plus pi r square. So here this can be simplified. Pi r square plus pi r square is 2 pi r square, which can be further simplified to take 2 pi r common, or h plus r. Interchanging r and h, I get 2 pi r into r plus h. Therefore, total surface area denoted by TSA of a cylinder is 2 pi r into r plus h unit square. Is how we understand the total surface area of a cylinder. On the top and bottom included is 2 pi r into r plus h unit square, where r is the radius and h is the height of the cylinder. Now that we have discussed about a cylinder and its curved surface area and the total surface area, now comes the next three-dimensional solid object called a cone. We all have come across a shape when we were wondering what could be the shape called in mathematical sense. Imagine we went to some ice cream parlor and we had a cone ice cream. So here we bring into concept of a cone ice cream, which very much defines a cone. So the cream out on the top, but as we see this, we clearly see this shape has its specific definition in mathematics. The cone, what we're talking about in cone ice cream, is nothing but which defines a cone in mathematical sense. A cone which looks like this without the cream would look in this manner, and such a shape is called a cone. This shape is called a cone. So what is a cone? What are its different properties? As clearly we see that each of the circles, just like in the previous problem, we had a cylinder taken as a real life model. Each of the discs, which was of the same shape, have been constructed to form a different shape called a cylinder. Now next we will investigate on what happens if I start reducing the shape of the CD as I go down. The first CD which is on the top, then the next CD if I put is a little smaller in size, then we get a shape which is quite different from a cylinder. Cylinder has all CDs of the same size, but a cone has all the CDs which are decreasing in size. So here I take a CD, then I take a smaller CD, the next smaller, the next. I get a kind of a shape which is called a cone. So a circular regions which are placed in decreasing order until they reach to the 0 point is how we define a cone. A cone is a solid object obtained by set of decreasing circles until the size of each circle until the size of the circles reduce to 0 is how we define a cone in the mathematical sense. A cone is a solid object obtained by set of decreasing circles until the size of the circles reduce to the point which is the 0. So here at this point we call this as point 0. Through this point 0 we get a cone which is in the shape of a V-shaped object. A cone derived from an ice cream cone is understood in the mathematical sense through this definition. Set of circles diminishing to the point 0. Now that we have discussed about construction of a cone and understanding of how a cone is constructed using the circles, now let's enter into understanding a right circular cone. So what is a right circular cone? A cone which is exactly 90 degrees and circular in the bottom. So a cone here which is exactly 90 degrees with the base and this being a circle are the two important points which make a right circular cone. So a cone whose base is a circle and if the base is perpendicular to the height of the cone, then we say such a cone is a right circular cone. So let's take the definition of right circular cone. So here the definition says cone whose base is a circle and which is 90 degrees and whose height is 90 degrees to the base is called a right circular cone. Is called a right circular cone is how we understand a right circular cone. The base is a circle and the height is perpendicular to the radius. It's a right circular cone. This is not a right circular cone because its base, when connected with the height, is not 90 degrees. The angle made by the height with that of the base is not 90 degrees. So this is not a right circular cone. And this is a right circular cone. Now that we have understood a right circular cone, let's try to understand the curved surface area. What is the curved surface area of a cone or a right circular cone? So this session is about curved surface area of a cone. So let's see the curved surface area of a cone. Here is the cone. Here is the radius and here is the height. So we have a relation which says because it's a right circular cylinder, this is 90 degrees, and I have here the slant height L. So I have three different dimensions: L, which is called the slant height of the cone; and R, which is called radius of the cone; and H, which is called height of the cone. Slant height, radius, and height are the three important things which define the curved surface area. So the curved surface area is the curved region of the cone, which is exactly the curved part but not the base. So curved surface area denoted by CSA of a cone is pi r. And R is radius, L is slant height, pi is 3.14 approximately. Curved surface area of a cone or a right circular cone is pi r L unit square.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.